Please allow me to introduce Dr. Bill Philpott. Dr. Philpott is a professor in the Civil and Environmental Engineering Department at Cornell University. While his field is remote sensing, his perspective is in changing and understanding the interaction of light with the Earth's surface, such as water, vegetation, and soil. He began as a graduate student in marine studies at the University of Delaware studying coastal oceanography, but has come to consider other water and land applications including agriculture, forestry, geology, and others. Bill's current interest is in characterizing wet soils. Bill will be presenting on spectral reflectance of wet soils, implications for modeling.
Thank you. And oh, wow. That's bright. Can you all hear me? Or should I wear a microphone?
You're good.
Okay. Something that occurred to me is when I was a graduate student in oceanography, I wanted to do field spectroscopy and called around to companies, and this is in the 70s, to see if I could find one. And was met generally with about 5 seconds of absolute silence because they did not exist. I really do appreciate these instruments, just as a note. Okay, yeah, I'm interested in how wet soils affect spectral reflectance. And I've been using this slide for a long time. It's the best one I've found, and it's right north of Cornell. It's in Ithaca. But you can see the drainage patterns in the soil. Because I've been saying because they're wet. And, oh, I also need to introduce Cha Tian, who is sitting back there. All of the data that I'm going to show are data that she has collected and were used for her thesis, and she's continuing on, so I'm usurping much of her work. But at her thesis defense, one of the faculty members said, you know, that isn't necessarily wet, because water brings different materials as it drains, and it deposits them along the way. So that could be dry soil with different materials. I say it's wet. Okay. And spectrally, if I could look at that spectrally, I could prove that, but I have to make that point now. Okay, but wet soil darkens, water darkens the soil. So what I'm interested in is what are those spectral changes and how does that tell you more about the soil? Not just can you pull out the wetness, but can you tell something about the soil itself? And just want to understand what's going on there. Okay, whoa. All right. I'm going to repeat some slides that I showed at an ASD symposium 6 years ago. Is it me?
Reseat the connector.
Okay. This could be an exciting presentation, I guess, in the ways I don't intend. If I don't touch it, the spectra that you're flickering at you is data from Lobel and Asner of 2002. And they collected periodically, as soil dried, they collected spectra just to come up with a model and some description about what was going on. And maybe there's another connector here that would work. Is this? Pardon? Why do you do that? Okay. Sorry about that. Looks stable? Okay. Some things to point out. This is, the black line is the saturated soil. So it's, the blue line up here is air dry. I'm sorry, the gray line is air dry, the blue line is oven dried soil. Okay. So first of all, soil gets darker as you get it wet. Now, this is the visible. This grayed out area is the visible. So this is what we're seeing. And yeah, it gets darker. Eventually, before it gets too wet, it just gets stabilizes in color. That changes. You get much more range when you get out to the infrared, and a tremendous range when you get to the shortwave infrared in the change in color. Now, I was coming at this from an understanding of water, and when I looked at that, I thought, that's just the water absorption spectrum. That's all we're seeing. I can model this very easily. No sweat. Easy. And I did. And what I got was a set of models. These are the 4 data sets that Lavelle and Asner collected. And my model is the dotted lines that overlay that. Okay, not bad, but it was honestly, it was a terrible model. It's not good physical ideas. It was just throwing something together saying I can match those curves. And I'll point out where I can't. In here, in particular, I could not match that consistently. In this particular case, it could. Here, not so much. Here, it's particularly bad, and it missed. I was missing some very important physical properties of the soil. So that model was crude. It got my interest, and I finally found out how complicated soils were and moved on to looking at this. Okay. So this is my favorite slide. Just because it fits doesn't mean you can believe it. Okay. All right. These are the 3 soils that Chad measured. We chose those because they are so different. We have the quartz sand, which is very large, coarse sand, the masonry sand, which is relatively fine sand and darker, multiple materials, and then Ithaca soil, which is sort of typical soil of this region, a very, what's it, a clay loam, silty loam soil. It's so very small particles, very different colors. So we've got a range of things going on with this. This is our setup. This is our goniometer. This device here, homemade, very much like, well, homemade. It's like chips in that it's homemade. It's not like chips in that it's much simpler. It's just a one-dimensional piece. But the thing is, we were using an 8-degree field of view, looking at the soil sitting on a scale. We measure the amount of water that's remaining in the sample by weight. So it's filled, it's saturated, and we watch the soil dry. So that's what we do. We watch soil dry. The basic idea is it's a fairly large sample holder, field of view of the 8-degree field of view detector. We're now using a 3-degree field of view detector to get in there. Also wanted to have a microscope to watch the thing as it's drying, because this is kind of fun. A movie of soil drying, right? That'll be my next YouTube video. In order to put the water in and not disturb the surface, you have a little port on the side that inserts the water at the base so the water can infiltrate up. The idea is to minimize the amount of air space that holds out in the pores. If you pour in the top, you could get potentially some remaining air spaces in the pores. Hopefully, if you put it in at the bottom, it's absorbed up, it percolates up and fills all the spaces and becomes as saturated as possible. Back to the water absorption spectra, it's showing this in a little bit different form. I wanted to point out that there is a 6 order of magnitude difference in the range of the absorption coefficient from the visible, from the blue range, up to the shortwave infrared. That's a huge range. Things are going to be looking very different depending on when you're looking, which range you're looking at and what characteristics you're checking. So, and I want to point that out and sort of draw some implications from that. Okay, these are the spectra, or selected spectra that Cha made. And this is the quartz sand up here, the masonry sand here, and the Ithaca soil here. Wet to dry. Notice that the quartz sand starts off slowly, doesn't change much for a while, and this is a constant. Let me describe something here. The evaporation rate is constant. All the water loss is through evaporation. We have a sealed sample holder. All the water loss is from evaporation. It's drawing up the water from the volume, keeping a fairly uniform water surface, and constant evaporation rate up to this point. Constant evaporation here, up to that point. Constant evaporation here, up to this point. All of this change it's not a uniform change with the rate of loss of water, which was interesting right away. But look at the differences between the soils. This goes up, stops, basically, looks the same for a while, and then slowly increased in a huge jump in a very short period of time. These are 1-hour intervals. With the masonry sand, it basically does not change initially, gradually changes, and then huge leap. With the Ithaca soil, the very small particles, first of all, it's saturated and doesn't change. It just hangs out. Then the water content begins to change. It changes almost steadily until here, and then a leap. Okay, so something's very different. Primarily, it's the particle size distribution. It's the pore spacing that's different. It's changing the way the water is held in the soil. And that's changing the reflectance properties. Okay. Let me go back. Okay. It won't go back, so. Well, it will go back slowly. Cha looked at this and thought, what's the most sensitive? Right here. Here. At the water absorption bands. That should be the most sensitive to the water content. Why don't we look at that? And the idea was that, well, the more water there is, the deeper this depth of this feature should be. So as the water content increases, that should increase. That height should increase. And this is sort of the model that we were thinking of. This is at the 970 and 1160 nanometer water absorption bands. And yeah, that's what you're getting. We only saw this, though, with the quartz sand. So this nice linear change, or nearly linear change with reflectance to water content was there. What we saw with the others, first of all, in the other sands, in the other soils, we didn't even see the water absorption band at 970 and 1160. It wasn't there. I'll explain that in a minute. We did see it at 1440 and 1930, but it was not a nice, simple relationship with the water content. And this was problematic, particularly here. where instead of the depth of the water absorption band increasing as the water content increased, it decreased. This is not good. This was not our idea. So the next piece was to model this, try to see if we could describe what was going on with this very little. If the other order, if the first model was a 0th order, this is maybe a half order model. It's just a little bit better. But the idea was radiance coming in, a little bit reflected off the surface, air-water surface, some absorption through the water, reflected off the soil-water interface, back up through the water, some reflected, some lost right here at the water-air interface, and measure that. That means that we get the reflectance is just the downwelling irradiance and the upwelling irradiance over the downwelling irradiance, and we get then one reflection from the water-soil interface, two reflections from the water-air interface, and the attenuation through the water. That's it. Very simple. Just a layer of water over a uniform soil surface. And what we got was the curves down here. And to my surprise, they look an awful lot like the curves that we got for the soil. We have this nearly linear transformation for the 970 and 1160 bands, this slow curve for the 1440 band, and the peak and quick drop off for the 1930 band. So it could explain a little bit of what's going on. And let's see, that's the quartz sand. Okay, it's not a great model. I'm not suggesting that you use this really absolutely apply it, but it gives us the right shapes. It gives us the right idea. Oh, and then if we take the derivative of this difference with respect to the thickness of the water layer, you can solve for the thickness of the water layer at that point. And that tells me that roughly it's going to be at about 100 microns. When you get a water layer that thickness of 100 microns, then that's going to be a peak. Well, probably what's happening is that the bulk of the water has sorry, I'm having a little trouble learning this. The bulk of the water has gone right in here. The water is absorbed onto the particle surfaces. It's not in the pores anymore, and that's what we're seeing, and that's where we're getting this very thin layer of water. One other piece on this is that this is the evaporation rate. So computing the evaporation rate and just monitoring it over time is virtually constant for all three soils for most of the drying period. At the end of the drying period, it takes a dive. Here, there is pore water, and it's feeding. Let me describe what's probably going on. It's saturated to begin with. The soil is absolutely saturated at the beginning. Only losses from evaporation. If some water evaporates, it draws water up. The capillary forces are greater than the gravitational forces in the water and the soil surface. So it just pulls water up. Eventually, some air pockets form in the soil. And it's not uniform. An air pocket will appear in one spot, an air pocket will appear in another spot, usually in the larger pore spaces. So they'll show up there first. Eventually, all the pore water, the available pore water will be gone. There'll just be meniscus in between the soils and water absorbed onto the soils. At the end, that water eventually comes out, and all that's left is the absorbed water, and then that goes. What we're seeing here, right here, is we've gotten to the point where there's only absorbed water, and that's dropping off. So we're getting a change in the evaporation rate. It's decreasing at that point. Up until that point, there's always some liquid water to draw from, and then you lose it. Well, entirely fortuitously, This drop-off occurs at the same time as that. We're looking at different things. We're looking at reflectance and we're looking at evaporation rate, and they happen to coincide when the water adsorbed to the particles is disappearing and you're starting to see some particle left over. It happens with all of the soils, no matter what, even though the timing is very different with the volume water content or with the actual time. We're seeing the same sort of thing going on. And it's here is where it happens. Here is where it happens, and in here, between the brown and the, it's a slower change here, but it's the same thing going on. Okay. So we've got some physical relationship between the change in reflectance and what's going on with the water in the soils. Let's see. I think that's okay. So I had a few implications. First, water absorption in the shortwave infrared. Water absorption controls the change in reflectance. Let me go back one slide and point out something. I can't see it well here. See this feature? That's a soil absorption feature. That appears when the soil is dry. Notice that it disappears as we go down, and it doesn't take much water to wipe that out. The water absorption is wiping out the soil characteristic features. They're gone. That even happens here. Let's see. Yeah, here. You can see it better in the masonry sand. That's the soil absorption feature. It's gone. So water's controlling the color change in even on both the magnitude and in the subtleties. It's controlling the reflectance characteristics. Soil spectral features are masked by the water absorption, and water masks the soil. The water optical path is a useful metric. So and that's going to be a spectrally changing thing. How far is the light getting through the water before it's pretty much gone? I could go into that more if anybody's interested later. But okay. Water absorption is strongly wavelength dependent, so we're going to have different types of effects in different ranges. Notice we really couldn't see the SWIR1 absorption bands, if you will, the shorter wavelength absorption bands, in anything but the quartz sand, because the water optical path was only long enough in the quartz sand in order to be able to see those absorption features. In the far longer wavelengths, we could see the same. We could see the absorption bands in all of the soils. Then water optical path is going to be related. It's going to be related to the size and distribution of the particles and the size and distribution of the pore spaces. The rate of change, the characteristic bands that are available and the way they change are going to be related to the pore spaces and the particle sizes. The disposition of the water. Where is it? Is it liquid water in the pores? Is it absorbed on the surfaces? Is it in menisci in between the particles? So those are going to be controlling that, which also suggests that this should change with angle. We have a goniometer. We haven't used it we haven't made all the measurements at angles yet, but we expect significant changes in the spectral reflectance as we change the viewing angle and as the water content changes. Okay, I've got to move a little more quickly here. Go back to this, the water absorption. Okay, here, the water optical, the attenuation length, they've got an absorption of 0.1 per centimeter. So an attenuation length over a millimeter or so. In here, there's virtually no attenuation by water over these lengths. We've got millimeters at most of water. It's not going to be absorbing. It's not going to be scattering. It's got to affect the reflection in some other way. And just to prove it, in the visible, even in the red, this is about a foot-deep tank, and we can see every possible color within our visual range, from blue to red. Water's not terribly removing much of the light. At 10 meters, if you're a diver and you go 10 meters, yeah, red's gone. But at a few millimeters, no, it's there. So is the shortwave. So is the very near infrared. It's there. Water's not absorbing. It's not long enough path length to scatter much. It can only change the color of the water by changing the relative index of refraction. So the light comes in, it's more likely to be scattered forward. It's more likely going to change the interaction there. What's happening is that it's enhancing the absorption by the soil. Or that's my hypothesis, at least. So my hypothesis here, absorption and scattering by water, pure water, is negligible at these distances. The darkening results from soil absorption and improved soil absorption because there's more multiple scattering, light's getting deeper into the soil, more opportunity for absorption, more light's absorbed. But it's absorbed by the soil. And then, since the particle diameter is much less than the wavelength, and the wavelength is, much less than 1 micron, and the wavelength much greater than 1 micron, particle sizes are much greater than 1 micron. The wavelength is much less than the micron. I'm going to assume that the scattering phase function is constant over this range, over this wavelength independent. I don't know what it is, but assume it's constant. So the veneer color of the soil will not change as the reflectance decreases. Okay, so no color change, just amplitude change. And now, probably everybody here knows the vegetation index, the normalized difference vegetation index. But this is in Maryland. This is Delmarva Peninsula. This is hyperspectral imagery. This is just 675, the red versus the infrared band at 877. The scatter plot has been converted to reflectance, so the NDVI should work. Along the diagonal would be an NDVI of 0, and an NDVI up to 1 up here, and here's a soil line. And if I block that out, oh, I got this. Okay, I've got 2 different types of soil. I've got outlined in green here and outlined in blue there. I've got the bright soil and the darker soil. Let me go back so you can see. I have 2 types of soil basically here, outlined in the scatter plot. And I can outline them there very neatly by just, my hypothesis then is that the main difference here is from dry to wet, from dry to wet, and that will obtain in every spectral band through the visible, through the near infrared, up to about 900 nanometers. As long as the water absorption is low enough. So that line, it doesn't. Maybe it's not just dry to wet. Maybe it's a little different material in there, but that's the idea. Okay. If that hypothesis is true, then if I took the principal components analysis of those spectra of the soils from wet to dry, the first principal component should have 99% of the variance. And most of the variance that's left over, explained by the remaining principal components, should be pretty much random. Okay. Well, this is using Chow's data for the quartz sand. It's pretty linear, as predicted. It falls along the line, the radial line to the 0, 0 point, so there's no color change, at least in these 2 bands. So far so good. Go to the masonry sand. It's not bad, but point out that there's a little bit of a curve here. It gets a little brighter in the infrared, a little dark, and then darkens down here. It's also a peculiar increase. It gets darker, 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 and then brightens. Anybody have any ideas what that is? I'll show you in a minute. All right. And then the Ithaca soil is more shifted. It's more infrared than red than the other. So the color, the basic color is a little bit different, but it follows follows that basic line also has a return. You can see it strongly there. This is supersaturated soil. It's not only is the water in the pore spaces, it's actually on the surface, making a continuous water surface. You're seeing specular reflection from the surface. Here. So you can see dry, drying, wet, and saturated. This saturated is actually brighter than that, just because of the specular reflection on the surface. So I really shouldn't, this is oversaturated, a little bit too much water. It's almost a continuous water surface, and the orientation of the surface is directing water into the detector. That's why you get that last little bit of increase. Okay, but basically the color has not changed. It's brighter to darker, but the color has not changed. If I look at the principal components of the spectra, this is the first principal component versus the second principal component, but no scaling. This is scaled to stretch the second principal component. This is virtually linear. So there's no appreciable change in color as you're adding the water. These, by the way, are the eigenvectors. So this shape, the blue, is the first principal component, the first eigenvector. It's basically the color spectrum of the soil in this range. The second eigenvector, the red, is a contrast between the infrared, which is positive numbers, and the red and the visible, which are negative numbers. Third principal component kind of contrasts the middle range to the end ranges, but it's noisy, and the 99.7% of the variance for the first eigenvector, the first principal component, less than 3% of the variance in the second principal component, and marginal amount in the third principal component. We've got 500 other principal components with less. Okay. This, by the way, is the dry to wet. Okay, this is not noise. There's something organized going on there. I don't know what that is, and if anybody has any thoughts, please let me know. I don't understand why that's not just random noise. The next, we go to the masonry sand. Again, I have 99.8% of the variance explained by the first principal component, less than 0.2% explained by the second principal component, and some really trivial amount in the third principal component. Again, the blue line is the first eigenvector, and that's essentially the spectrum, the reflectance spectrum of the material. Again, there's a contrast between the visible and the infrared. The sign has changed, negative to positive, but it's basically just a contrast. And the third principal component, I'm going to pretend is not there because it explains so little data. But this, now, the second principal component, there's structure there. Something's going on. Something's changed right there. I don't know what that is. So but there's something happening with that, the structure of the soil that's different. This is almost two linear lengths. This one's a continuous curve. I have no idea what that difference is, what could cause it. Last one, the Ithaca soil. Again, 99.9% of the variance by the first principal component, less than 2% for the second, and something, again, very trivial for the third. And the second principal component, it's very small variance, but something's going on. Okay, my conclusions. I think my hypotheses were basically right. Absorption and scattering of pure water is negligible. It's really not affecting it affecting the spectrally directly. It darkens the soil, darkening the result of soil absorption, and that's explained by the first principal component being 99.9% of the variance. And the veneer color does not change as the reflectance decreases. doesn't really change, subtly. There is coherent color information, though, in the second PC, so there is some color change. Represents a contrast between the near-infrared and the visible. So it's got to be either subtle water absorption effects or some wavelength dependent of the scattering phase function. Or maybe somebody else has another suggestion. No hands going up.
Yeah.
You done?
I'll wait till the end if you want.
Okay, just I'm basically there. This is my last slide. Oh, and yeah, that's the last slide I intended to show. All right. Then I'll be happy to take questions. Yes.
Oh, no, go ahead. You're fine.
One of the amount of scattering you get at each, you get scattered anytime there's an index refraction change. And when you put water in there, you replace the air with water.
Right.
And the water doesn't have a constant index of refraction across the wavelength range. But if you look at the wavelength dependence of index of refraction of water, it actually has the same shape, very similar to your second PC. So I'm wondering if that isn't...
You might have something there. Right. That would be interesting. Wow.
So.
Okay.
Because so the amount of scattering you get off those grain water boundaries is going to have a wavelength dependence because the index of refraction of water changes.
You know,
from 400
you're absolutely right. I've been thinking of the index of refraction of water being virtually constant.
No.
But neither that or the soil is constant.
Right.
So
well, and every mineral
combination-
grain is going to have its own little index of refraction function, and so it's the bigger the contrast, the more scattering you get. So the interaction of the index of refraction function of the water and the grains themselves will.
Nice. Thank you. Okay. Do we have time for one more? Yeah. Just.
Yeah, actually, two points. Some of these subtle water absorption effects that you were hitting on across all the different materials or all the different samples that you had could be explained by the clay content or the fines content. Did you look at that?
For the Ithaca soil, that's true. For the others, there was for the quartz and for the masonry sand, there was very little clay.
Okay.
There was very little organic material.
Yeah, and then the other thing, it's my background is more from the soil mechanics side of things. So seeing sort of the measurements that you took over time, I think would be very interesting to look at from a water content or percent saturation point of view, as opposed to because you're drying in a heterogeneous manner. You saw on the surface that one area was dry and one was not, and you're sampling that. But I think it'd be very interesting to actually create more of a homogeneous sample out of for each one, and actually just have one value of the water content in each sample.
I may need to talk to you a little bit more about that. Okay. All right.
Dr. Philpott. All right, and now please allow me to introduce Dr. Joe Kiter. Dr. Kiter is a research associate working at the program of computer graphics at Cornell University. He received his PhD from the University of Pennsylvania, and his research focuses on interdisciplinary digital design of sustainable architecture. He works on advanced numeric simulations that calculate a building's daylighting behavior, thermal performance, and material properties. Dr. Kiter will be presenting on measuring skylight for sustainable design.
Okay, thank you, everybody. I'm pretty sure everybody probably can hear me too. I want to thank Chip and the members of ASD for bringing us all together here. One thing we always talk about at lunch and every time we get together is a lot of times with these spectral applications and properties and things that we're doing, we're using a lot of the same math to attack similar problems, but coming at it from different angles. And I'm going to come at it from a totally different angle than what you saw with the soil work and with the volcano work. We're trying to show what we're doing for rendering and sustainable design. So I come from Cornell University, and at Cornell, I work with Don Greenberg, who is one of the premier members of computer graphics. And Don's lab's been working on a variety of rendering problems for the last 40 years, from this article in Scientific American to some recent rendering work we did last year. Now, The difference that Don tries to do with our lab, and it's a philosophy that I've adopted and a lot of people have adopted that have come out of our lab, is we're really concerned about what we're actually producing is correct and not just making the pretty picture for a Pixar movie or a DreamWorks movie or a Disney movie. We want to take something that we know exists and be able to perceptually validate it and physically validate it. So this was an early experiment back in 1970. Granted, it's only a box, but for 1970, this was a big deal to actually validate something. Nowadays, obviously, we want to validate large vegetation and a lot of different movies for buildings. So Don initially set up to do his bidirectional reflectance function validation, go near reflectometer that did things in the visible range that measured basically between 360 to 720 nanometers, that was set up with 3 degrees of freedom, so it could do things that Chip was thinking about doing when he took his measurement device out into the field of rotate the light, rotate the sample, and rotate the camera to get all these different angular dependence of light reflection for card paint, for drywall, for cloths, and all these other interesting materials. Now, we've moved on in the last 40 years to do some stuff with architecture to be a different application. And the way I pitched this is we're still doing things for computer graphics, so not just rendering a movie for Pixar, but taking those same couple wavelengths of light and moving it out of the visible and moving it into the IR so that we can do things for daylighting analyses, do things for sustainable design, to do thermal studies. So when you design a building, it actually can have some impact on what's going on. Now, sustainable design has started to become a little bit of a dirty word, I would think, because people are throwing it around way too often. So, if I just put a tree in front and then the tree goes away in the winter, I now have sunlight coming in and they're trying to say, oh, this is going to make your building better. It's very similar to the early days of computer graphics, where I can make a very pretty picture, but it doesn't mean it's radiometrically accurate at all. So, what we want to do is be able to use the knowledge of rendering and computer graphics to create buildings that can actually impact and have sort of this net zero impact on society so that you feel comfortable where you work. You're not just in an enclosed space. There's big office windows, there's daylight coming in, you feel comfortable thermally so you're not too cold or not too hot. There's micro zones inside of there, and we're moving from basically simple zoning to more of these micro zones. This is an example of a controlled environment in California where they have birds flying around, and so their own microenvironment, they use this daylighting to funnel into the area and get the properties that they want. Now, the interesting thing about this is after they built it, they had an idea of what was going to happen, and what happened in reality was totally different. This is the problem we're trying to solve, is the model that you simulate is validated such that you actually get it when you actually build it. And this is something that has not been done in the architecture field, in the computer graphics field, and something that we're trying to create. So you don't have to sort of create different fixes for it after the fact. Another fact is buildings are going to become more modular as they grow in different parts in the future, where these facades will start to be dynamic. They'll change over time and allow different daylighting in. So if you have something in Ithaca in the winter, or in Rochester, it's the same problem. It's very cloudy from October to December. When Don brought me up to recruit me to Ithaca, it wasn't California skies. It's gloomy. They don't really tell you the sun's going to disappear for 4 months of the year. We want to be able to actuate these facades so that it lets more of the daylight in the winter and less in the summer. So you're not having this glare problem when you're looking at your computer. So the efficiency of your building is going to interact with this device. Now, there's a whole bunch of metrics that people use, and you might see a building is LEEDs rated and all this, wonderful things, and they have all these metrics. Not one of these metrics are validated, so these metrics are, blah, blah, blah. So these are examples of some buildings right here in this yellow space that are LEEDs Gold, LEEDs Silver, LEED Platinum. They are supposed to be the most energy efficient, the best buildings in the world. And they are not doing, they are actually losing the net zero quality. They're really expensive. They're not what the people intended. Again, the point I'm trying to get across is just because you say something is great, if you don't validate it and find a methodology to doing that, you're not actually going to produce something that you would expect, and it's not something that's wrong. So what we're trying to propose in our lab is to have a simulation that we can go out and validate, and this is where the ASD device is invaluable, where we can go out and spectrally validate our model to say what we're getting is what we have, see some of these buildings go through the design process, and also validate them inside to say, you know, what we're getting is what's actually happening. There's a global need for this. I'm not going to go over this too much. It's just saying that two interesting factoids I learned from working on this project is that half the buildings, high-rises that have been built in the world have been built after 9/11. So in the past 15 years, half the high-rises that existed did not exist before. There's a massive move in India and in China to move away from the rural and move into the urban environment. This was a picture I took when I was in Shenzhen last year in China, and I just looked around. I have friends that are glaziers looking for work in America, and there are 8, 9, 10 cranes going up in Shenzhen left and right, and there's, you know, tons of buildings going up. We want to make sure that when these buildings go up that they do have a good green quality to them, they are sustainable, and the people in them are comfortable as they go through. So when we have this design process that goes, an architect will sit down. Now we're all engineers, and you know, we have our design process. When an architect sits down, they have this idea of a conceptual design. They're going to go through a form and space. So some architect looked at this room and said, I want to have a tiered structure because the students will have a better view and nobody's head will block. So if some guy 6'4" like me sat in front of somebody short like Bill, I wouldn't be blocking his head as he's trying to look over his talk. But they do it really quickly. They spend a very small amount of time in these two steps, and they spend a large amount of time in the construction part. So they don't have a lot of time or budget to go back through their iterations when they want to make something green, when they want to do some of the simulation. So a lot of this stuff doesn't actually happen. So what we're trying to do is do quick methods that are validated that can affect early phase design, so an architect can sit down and say, well, this is letting more daylighting in, I know this is going to change the thermal properties, how, and everything can sort of happen in a streamlined effect. I'm just going to just skip over that. So my main problem with our simulations are, when you put a bad simulation model in, you're going to get bad data out. This is sort of what models currently happen. So I would contend that most architectural weather simulation models are wrong. And they're wrong in the fact that they blur over a variety of interesting details. So for example, if you have a cloudy sky, most architectural weather models would just say it's just a blurry Ithaca or Rochester sky where it's uniformly gray across the sky. Most people know that that's not what actually happens. Skies are very rich. Earlier we showed an example of some cirrus clouds where we saw they were isotropically scattered throughout the sky, and it wasn't a uniform illumination, so these assumptions are actually incorrect. They oversimplify these models of clouds, and we want to produce more interesting volumes into these weather models. And we want to make sure that they're validated in that effect. Additionally, these models do two different things. They do one thing for the visible range, and they do a whole different thing for the infrared and thermal ranges. And what we're trying to also say is, why have these different inputs? Why have two different models? None of them are validated. You're trying to mix and match things here. All of these are used wavelengths of light. They all use this radiative transfer. It should be one unified model that goes from doing things in the visible that moves into the infrared and are simulated all as one model interconnected. So the main thing we're trying to do is measure these all-weather skies. This is my piece of the project and the part that I spent the last 3 years on trying to do. And this is a kitchen in Ithaca, and the main thing that I'm trying to show here is that skies have a very unique impact, especially here. You see the harsh glares coming in on the kitchen. They're bouncing off the materials, bouncing all around. And over here, it's more diffuse, more shadowing, more distinct light. Adding clouds into the equation, you see it sort of goes from being really light from a clear sky to being really dark for an overhead sky. So clouds play a significant role in this illumination, but they also have this directional component associated with them where it's not just uniformly dark across the whole sky. And I can't just blur light 20% or 10% and hope to get the right answer in the end. So what we're trying to measure is basically the light on the surface of the Earth. This is something we're all familiar with, which is sort of a stock slide I have, where obviously the light is following this black body on the top. We're trying to measure it from the ground, but we're taking the ASD device and sort of pointing it up at the sky. where in general, a lot of people are concerned with the irradiance for skylight. And that's great if you're doing outdoor scenes, yearly averages, and all that. We're primarily interested in this cone or directional component that Chip was talking about, or we're calling the radiance, such that if you have these harsh glares and light, this directional component to light is essential if you're having a building and orienting it in space in some form. So our work uses basically creates a multi-acquisition device where I capture a series of HDR images. I use a spectroradiometer. I have an irradiance sensor set up. And I create this data set that basically allows us to have a multi-tiered capture that sort of exists. To do this, I then simulate and try to fit analytical models and data-driven models to create better skies so that I can produce better data. And it allows for a robust comparison and validation so I know what I'm going to get both from the simulation model and also validating it throughout the architectural design process. So this is a series of our devices. We utilize the wonderful backpack ASD gives us as I climb up 5 ladders in various buildings of Cornell, and with all this stuff on my back and setting it up on our roof. So here we've outfitted the 1 degree 4 optics on 2 pan-tilt servo motors, such that we can scan any point in the sky dome that we actually want to. I have an HDR camera set up that gives me a fisheye of the entire sky, so I can show you those images of the skies I'm actually capturing, and a irradiance sensor so I know what the irradiance of the sky is actually sort of producing. Now, I was a postdoc, I don't have a big budget, so I do a lot of things with duct tape, and it's not as refined as Chip's model, because I don't have the budget he has, but it definitely works. So we basically have outfitted our own fitting devices to actually fit the ASD device. It basically can scan any point in space that we want to. I have a compass just to ensure that the direction I'm getting is what I expect, and 2 pan-tilt servo motors to actuate the device into any angle that I want. So it basically goes throughout the sky and scans any same pattern I want to actually do, so I can scan the sky and get the 1 degree radiance component of what that light is actually happening at any given point, which is very useful to both validate the radiometric properties of existing skies and evaluate radiometric qualities of my skies. We also have taken the data and also have a data-driven model, which is what we're sort of calling our ground truth model, which basically takes this data and actually produces a model that's not analytic, that's produced both from data. So we are using the older version of the Field SPECTRAL, so probably one of the original ones, which looked like it came out in like 2001 from your guys' slide. And we designed our own component here. This is just an old sketch that I had of trying to, fitting this together in my head. And a couple design models of how to fit this such that it doesn't block anything and moves around and gets us the weight and actuations that we actually need. And we control everything from our own Arduino so that we can program and do a variety of scanning methods that I'll get to in a few slides to show how we want to measure clouds versus how we want to measure the clear sky. So looking at the sky spectral data is really interesting. Earlier you showed one example of the radiance from the sun, and we're also interested in this sort of diffuse skylight that exists. So if I take the spectral radiometer and I point it at different orientations in the sky and look at it in a slice across the sky, we can see the different components of the skylight that actually exist. Now if I leave that same point and keep it for 20 samples over a 5-hour period, the light also changes. So this spatial and temporal aspect of the radiance that changes over time is what we're really interested in measuring and validating for our models, such that we can actually make sure that when you have all this light coming in, it's going to be what you expected in the building when you design it. Now, again, clouds also throw a big problem into it to make it more challenging. So the gray line shows the spectrum of solar disk that we captured. The orange is a cloud, and the blue is going to be the blue sky. Now the cloud is obviously going to be a little brighter than the blue sky because the clouds act as these big diffusers. So as the sunlight comes in, it's going to basically diffuse the light into a very large area. Not as powerful as the sun, but not as more powerful than just the blue sky. If we sample the sky and different clouds at different spots, we're also going to get different spectra, and that's also kind of interesting too to see that it's more powerful than the blue sky, but even going around, depending on how the light is reflecting off it or multiply scattering throughout it, you're going to have different properties of it throughout the entire process. So I'm going to just show you some examples of the better skies we're doing. It's not the focus of this talk, but what we do is we try to capture the sky with our device. We use this data to interpolate a whole bunch of points for the different samples that we have, and then interpolate in them to generate a data-driven sky. So once we actually have this data-driven sky, it's actually spectral across the entire hemisphere with this interpolation. So at any point, I can point into this and see what that light actually is going to give me, and then basically use that sky to basically have a daylighting model for a kitchen scene that is, I'm an engineer, so this isn't going to be as pretty as some of the architectural scenes. But it's pretty close to the kitchen we had before, where I can actually do these, harsh skylights and everything, and it's both doing a thermal model and a daylighting model all together. If I measure any point, I can sort of validate that it's actually working as well. Now, if I was to throw clouds into the mix, it's a much more challenging problem. So what we do is we go into the remote sensing community, and there's some wonderful satellites. Specifically, we're using the GOES 13 and 14 satellites to get us where they sense the cloud tops and cloud bottoms. They also give a lot of interesting information on the microphysical properties of the cloud in between to say, okay, here's what the extinction rate should be, here's a single scattering albedo, blah, 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 that we can fit into a volumetric model to create clouds. So what we do is we take our input of, we have, with the fisheye of what it should look like in this model from the GOES data of the cloud top and bottom, and we try to simulate and create a volume of what this cloud actually should be in the hemisphere. So we take this model, put it together, and we can create this volume, and then put that volume into our radiometric transfer simulation to try to get what the cloud actually should be, rather than blurring it to be one constant cloud across the entire sky. Once we get that, we actually can create accurate illumination. So this is an example of what this should actually be. So this is what we're hoping to get. This is what we actually get. It's pretty close. It's improving every time we actually get to do it. But the more important thing, if I take a point and I measure it, it follows the rough shape of what's actually happening. We're not quite there yet for getting the exact spectral match, but the spectral match is getting really, it's a lot closer than what it was, so we've taken a big step forward that way. But there's still a lot of improvement that we have to get it to be kind of exact to what is actually happening in the properties of the cloud. But given that we can only measure things on 1 kilometer scales, we're doing pretty good to match the shape and profile of our matches. Then, once we have this model, we can then use this to do daylighting and heating simulations inside a model. And then this is, again, a simulation that I recently just ran and submitted as a paper to show that we can create accurate daylighting in the previous picture model that I showed before. Here's just some matches to show visually what's actually occurring. Just to show you on top, these are photographs. On the bottom, these are our simulation models. What we want to show next is that we can take our photograph and our measured radiance and match it to our simulated model and volume to our simulated radiance. So this validation part, we basically, to validate this, take a sky model and scatter 25 points in a small region. Clouds move quickly. The ASD averages a bunch of samples. Everybody that uses the device knows you're not going to get a sample like that. It takes a second or two, and if I want to take 25 samples, it's about a minute to 2 minutes, depending on how many samples I'm averaging. Clouds could move dramatically in that time, so we try to keep a small volume and a small amount of samples to actually validate what we're doing. So here's just some examples of some close-up matches. So if I take this example of some stratus clouds, point the ASD device at these 4 particular points and look at the black measured curve averaged over 40 spectral bins. And the only reason why I'm doing that is because I'm simulating over 40 spectral bins, because the simulation takes a while to actually run. Initially, I just wanted to make sure that they're sort of accurate to show apples to apples. You can see that the general shape is being matched on what we're actually simulating to what we're actually measuring to show that our simulations are producing ballpark ranges of what the illumination should be. We're hoping to improve this even further by adding more and more properties to our volume and our scattering methods and our radiometric transfer methods inside our clouds. But we're pretty proud of where we got to, and the fact that this is generally doing 10 times better than anything that's been done in computer graphics or architectural visualization in the past 40 years. And we're actually able to produce clouds that actually have decent spectral matches. This is more of an Ithaca sky, or a sky we'll experience today in Rochester, or, your standard sky. And we're trying to also show, that it's not just one model. We have a whole bunch of different skies. We basically go up to the roof every time. Bill's going to lend us our device and go up and measure a lot of skies that show we sort of have this good validation. Now, just to show you an example, there's been a lot of different models proposed. Again, the red line here now is the measured data, and all these other models are going to be the variety of models that sort of have existed in space just for clear skies. And what we're sort of contending with this is that I'm sort of saying that all the models were wrong before, and we're making this big leap. This is kind of showing that all the models were all over the ballpark. Nothing was consistent, like this line is up here, and then on this angle it's down here. We're trying to show that our model is consistently capturing the shape and being consistent over all the angles we're measuring, and it's a lot better than what's sort of been done in the past. Previous models, if I sort of show it on a hemisphere and average it across there, have two major problems. They're really bad around the horizon, and they're really bad around the sun, and it's because they just are not able to handle the radiometric properties correctly or do the radio transfer simulations with any type of particular detail. And this happens for any of the samples that we were measuring for the previous work. So in the future, what we hope to do is provide these better solar and sky dome models that we're simulating and validating it with the ASD device and bring it into the architecture community of saying, okay, now that we have this measured long simulation model, we can create an analytical model from it and give it to you so that you can get interactive feedback in this early stage of the design process. So you can say, okay, I have a problem with my design here, or I have a problem with my daylighting design here, and I want to maybe put a dynamic facade in there or do something there for the thermal. So this is going to be great, especially as our buildings go from being stupid buildings to being smart buildings, such that you can basically think you can put maybe an actuated device in the roof of your building, fisheye camera, and you can use it to control and predict your smart building such that it can actually operate over time and adjust to the current conditions that are actually occurring. So this is something that we're trying to simulate now and hopefully trying to propose to Cornell to do for one of their buildings in the future. So whether you're building a new building, like this is Gate Hall, where they put all these wonderful fins outside of it for our new Grand Computer Science building. So I asked them when I came here, I was like, oh, these fins, they must block the light or do anything, and no, they do nothing but make it worse. They actually bounce the light into the building, and it makes it partly unusable. So what we want to do is not just do things that are aesthetically pleasing, we want to make sure these panels are actually put at an angle or actuated such that it actually blocks the light, maybe have devices up on the roof that controls this, and even if you're retrofitting a building, which is another building at Cornell we're retrofitting, allow these devices on here that can actuate the shades or the polarization of the glass based on what it's actually sensing both remotely and at the actual location. So in conclusion, what we're trying to do is take the spectral radiant measurements, and I'm a big advocate for saying that these measurements are important, that we need to validate our models such that when we know what we're simulating is what we're going to get when we design and build the building. It's great for rendering. We still have applications where Pixar knocks down our door and say, "Oh, you're doing clouds. We want to put, we fudge them in the Good Dinosaur. Can you show us what you're doing?" So we can create them in kind of future movies, and that's a great application too. And we want to be able to just say that we can give this data and these illumination models to a variety of communities so they're more accurate. So if we had a better idea of what was going on with the conditions of the sky, when Chip and Bill actually do some of their remote sensing, we can sort of say, we can build you the sky that's actually occurring. Here's what we think the illumination is. It might be useful to you guys to actually be able to understand what these changing sky conditions are actually happening. Because as the first talk sort of intuited, you don't have these days in Ithaca. There's no beautiful glory days in upstate New York. There's like 3 all year. And you have to be really careful to get one of them and go out and get it. We live in a cloudy sky. We live in a dirty environment, so we should be able to sense and simulate things in that environment. This is what we want to do is for sustainable design so that we can create these buildings that actually have an impact into the real world. So thank you for your time, and hopefully everybody enjoyed that talk.
Any questions?
Oh wait, there's a question in the back. Yes.
Can you go back to slide 39?
39. Wow. You really paid attention. Sure.
You only go out to 700. Any reason why you didn't show any of the...
Yes, okay, great question. My first and funding comes from computer graphics, so we're obsessed with the visible. So some of these graphs that I took are a lot for the visible range, but when we do all our measurements, they do both basically from 350 nanometers all the way out to 2,500, which the ASD actually does. We validated and simulated them for all these applications. However, since a lot of our funding comes from the computer graphics industry, they're just obsessed with the daylighting and visible models. It's the only reason why I'm just showing the visible graphs. I have more in a couple papers I can direct you to if you're interested in seeing what's going on. For clouds, it's really actually important and interesting. So the cloud stuff will have bumps, obviously, for the water content that Bill just talked about with his drying process. We experience the same issues with measuring clouds, with having these absorption and microphysical water properties there.
So did the other models that you compared against also go out into that?
They do not. So that's another reason too. We don't have no comparisons as well, which is a great point.
So a lot of these models just
stop at the visible. So again, the majority of these models are just trying to do daylighting studies and visible stuff. They'll have a different model that will just do the IR stuff. And what I'm trying to say with my work, and that's my sort of big pitch as I go around to doing some of these faculty talks, is I want to have one unified model. We want to put it all together and validate it all together and not have these two great simulations.
And they're all photons.
Yeah, it's all light, it's all photons, it's all Maxwell's equations. We don't need to have all these, mishmash of stuff together. It should be one sort of simplified model. But that's a great point and a great observation. Cool.
Well, thank you, everybody. We're going to take a quick break, and there's coffee set up outside, also back in the fishbowl just to the left as you exit the auditorium, and then we will meet back here at 2:20. Thank you. Okay. All right, thank you, ladies and gentlemen. And now, please welcome Naina Raqueño. Naina is a research scientist with the Digital Imaging and Remote Sensing Laboratory here at RIT's Chester F. Carlson Center for Imaging Science. And for the past 19 years, she has performed the thermal calibration for the Landsat suite of instruments. And over these years, this effort has required much field work, and her position evolved into the DIRS Field Campaign Coordinator, assisting DIRS students, faculty, and staff with their spectral measurements, requirements, and logistics. Naina's presentation title is 1999, Spectral Odyssey and Beyond.
So you can tell that I took this very seriously. I had a presentation set up, mostly on Landsat. And then I saw that I was the last presentation of a very long day. And I said, we're going to change this up a little bit. Oh, excuse me. See, it doesn't matter how many times you try things out, huh? We're going to change things up a little bit and talk a little bit more about the future. I'm not going to go all the way back to 1999, but I am a little bit. I'm going to do what you never should do. I'm going to actually read a scenario to actually kind of set the stage. But this journey actually began back in 1999 when we received our first ASD. We immediately took it out within days, like within 2 days of receiving it, and took it out on one of our largest collects under Avarice. We were very lucky to get a hyperspectral sensor overhead over Lake Ontario waters, and we went out and used it immediately with some success. And given the 2-day training, I think we did reasonably well. Back then, receiving the ASD back in 1999, it really was a sci-fi event. We really thought we had an absolute marvelous instrument that we thought we could do absolutely anything with this. And I immediately, I did not participate in that collect with the instrument, but within 2 days after that, we were out at Gannett Nuclear Power Plant measuring spectra with the ASD, and that's where I became one with the ASD. And we've ever since then we've been connected. Basically, because I found out that not all rocks are rocks, and I slipped and I fell into the lake. ASD was up here, though. From that day on, ASD knew that I was going to take care of it, no matter what happened. things would be okay with it, whether it meant that I was still alive or not. I would take care of that. So I'm going to start off this conversation with a little scenario, a little sci-fi scenario. It's just one example, but I want you to think about your own application, whether it be volcanology. We've already seen a great example for architecture. I'm going to talk about one scenario, and as I go through this and read through this, I want you to think about what we actually can do now, what we can't do, throw stones at this scenario, and what it's actually going to go ahead and take to actually get to that level. So I'm going to do what everybody says not to do. I'm actually going to read this. So students don't ever read in your presentations. But I'm not a doctorate, so it's quite okay. So it was a beautiful, beautiful fall day in the Finger Lakes in western New York, as a lake resident finally dropped her canoe in for one last paddle. One last paddle of the season. This is Canisius Lake down just south of here. As she was paddling along, she noticed that the water looked kind of odd. Now, she doesn't know much about water, but it just kind of looked like somebody had spilled green paint all over the waters. She had just recently signed up to be a volunteer watershed monitor, and she really wasn't sure what that was. Training doesn't start until next spring, but she downloaded the app to her phone and her watch, and she went on and she fired a couple pictures up. So she took these pictures with her little watch, and they were immediately linked up to a local monitoring system. She really didn't even give it a second thought. She really didn't know what she was doing. Again, she hadn't been trained. She didn't think about it for the rest of the day, and she didn't need to, because the location and the photos are automatically uploaded to the DEC lake monitoring system. So this monitoring system is in a constant state of modeling all the state's water bodies. It ingests satellite image. It is, as we probably have seen quite a few today, local weather conditions, forecasts, reports from citizens, and all sorts of watershed investigators. The model earlier that week indicated that the conditions were ripe for algal blooms in several of the western New York regions. But so far, no confirmed reports had materialized. So when that lake resident fired up the monitoring system, took those photos, the system was already in this kind of a state of alert. It was looking for any kind of harmful algal blooms. The images she took were no ordinary images, for the app knew exactly what specific wavelengths that would aid the identification of different water constituents, algae, and even cyanobacteria. The system immediately performed spectral analysis on those images, flagged a suspicious case of a toxic cyanobacteria indeed, and it indeed found that there was probably microcystins present. But that was just one report, just a single report from already acknowledged, uninformed, untrained observer. The real question is that whole lake actually in a state of harmful algal bloom? The monitoring system needed more information, so of course automatically it turned to the latest satellite image. And as we've already seen and talked about in this previous talk, pretty much cloud covered throughout. And the lake that I'm talking about is right here, Canisius Lake, one of the Finger Lakes. Furthermore, it actually went ahead to see what the next scene was going to be available from any of the satellites. And there indeed was going to be a satellite image later that afternoon. But coupled with local forecasts and modeling systems, it deemed that there's probably only going to be 25% chance that the scene would be clear. No big surprise. So, the regional DEC water inspector was notified, and the drone pilot. Again, just by the system. By the afternoon, the sunlight was dwindling, and the drone would only be capable of imaging a few sites, not the entire lake. The monitoring system identified 4 high-priority areas, 2 parks, 1 summer camp, and the intake for a local water authority. By the time the drone operator arrived at the lab system, the flight plans had already been uploaded to their system. And furthermore, there was suspicious algal bloom. The drone was actually, drone's camera was actually tuned specifically to those wavelengths, specifically linking to the microsystem. As the drone operator began prepping the flights, he thought surely he could save time and skip over the flights over the summer camp. This image was taken in late October. Nobody was going to be at the summer camp. He went on grumbling about technology being too smart for common sense, and then he received a text. There was a huge event planned at the camp on the waterfront that weekend. So he set off to deploy the drone with the auto-generated flight plans. Within minutes of landing, the imagery was uploaded to the cloud, mosaicked, and the local RIT Institute applied the harmful algal bloom algorithm that they developed. And immediately, just the map was actually uploaded to the DEC. There was no need for all the imagery, just the product. All they wanted to know was where the harmful algal bloom was occurring. So the map is just showing 3 specific areas indeed where that bloom was occurring, and that one long pond point was actually clear. So we'll go on to skip a bunch of this, but just a few years ago, you can figure that this scenario would be absolutely impossible. But I think today, we're actually getting quite close. With the addition of GIS integration, drone technology, obviously the spectral studies that we've been doing, we're actually getting quite close. Years previously, a report might have come into the DEC from a lakeside resident. They might have sent somebody over to investigate. They might have decided, it looks kind of suspicious. We'll take a couple samples, and then 3-4 days later, they would have gotten a report back. They might have just decided to close the beaches, especially around the camp, excessively, or they may actually just go ahead and just pass it off and somebody could have gotten seriously ill. We're going to talk a little bit about harmful algal blooms, but really the question is are we actually there yet? Whether it's this application or your own, what's it actually going to go ahead and take to actually move this forward? I'm going to talk just about a couple of different projects that we have here at RIT that kind of chips away at some of the problems of the specific example. So one of the obvious things right now that jump out is, okay, so we probably can't detect cyanobacteria with our cell phones right now quite yet. But those images that I showed, go back a little bit. There's clearly something going on in that water. Anybody could actually see just visually what that is, and we can actually fine-tune those sensors very soon. So maybe we can't quite do that, but back in 1999, we were just barely starting to measure the spectra of things, and we've actually come a long way. So I'm just going to talk about 3 topics that I think kind of chips away at this specific problem. I'm going to be talking about the Share 2012 Collect. I'm going to be talking about some of our Landsat 8 work that we've been doing, and a project that we just started that focuses more on this specific harmful algal bloom problem. Again, I'm going to be talking very high level. Each one of these could be their own couple-hour conversation. We won't have that now. The Share 2012 Collect has been featured at SPEED presentations for full sessions. So there's lots and lots of information I can share with you about that. So I actually lied. I'm going to talk about a couple other collects. That's just a quick image. Immediately, I just want to emphasize that we've always been using our ASD for a huge variety of projects, but we immediately started using it specifically for water applications in 1999. We've used it for deer simulations, our image synthetic scene model. We've been using it for even crime scene analysis. I'll be just talking just about a couple of those projects. I don't know why, but because we're at RIT University, we have lots and lots of students, every couple of years, we decide to have a really large collect. Let's just have a whole bunch of students go out, design all their experiments, and see what kind of sensors we can actually fly over that and have them have plenty of data. So one of these examples was Mega Collect 24, and it's called Mega because it was actually feeding Mega Scene for our DeerSig data. It had two different types of hyperspectral. It had long wave HSI, which at the time was unheard of. Extensive ground truth, probably about 50 different people, probably about 10, 15 different types of experiments. Data distribution turned out, even though they were promised to get us the data, it actually ended up being restricted. And we had unbelievable time actually trying to even use the data, and worse yet, publish the data, which is really important when a student's trying to graduate. Again, flash forward to 2010. We tried to do this all over again with SPECTRAL data. And this was data they were going to be able to be in the area, fly over RIT. We did a whole ton of different types of experiments, extensive field campaign, tons and tons of spectra measured with it. And did I mention it was kind of a freebie? SPECTRAL, actually they were in the area and they were going to basically do this at cost, just flight time. Awesome, that was great. Not so much. The idea of share was to actually be able to share and release the data to the actually whole entire community. But unfortunately, the data wasn't quite up to snuff for SPECTRAL, and they did not want us to release the data as their golden data set. So our huge effort in 2010 kind of fell flat when we actually couldn't release the data. We were still able to use the data in-house, but not showcase it as our huge, large collect and data dissemination to the whole community. So the recurring theme here in remote sensing is lack of excellent data sets, lack of imagery, and the corresponding ground truth. And so, I don't know why, but we never give up at a university. They decided to actually go ahead and do Share 2012. So just 2 years later, let's try this all over again. But this time we're going to pay for our own data. So a huge expense, we paid for our own SPECTRAL flights, and that way we could share the data to the community at any point in time. It was our own. So Share 2010 or 2012 was just a multimodal image collection with a large field campaign. Had a great graduate student help me coordinate this effort, Anne-Marie. And the main emphasis on this was in the name, was that to make the data freely available to absolutely anybody. So it was organized as a large multimodal collect over Rochester, New York, with extensive ground truth. Provide the community with all of this and actually disseminate the data as well. Obviously letting the students participate in the whole planning process and execution. Here are some of the different modalities of interest. As I mentioned, we had SPECTRAL, so we had a high spectral resolution sensor and a high spatial resolution. We had our own RIT WASP. We had also acquired Digital Globe and GeoEye, all of these sensors on the same day. We also had LiDAR, airborne LiDAR and ground-based LiDAR as well. And we had hoped for full motion video and long wave, and that was just cost prohibitive. Maybe for Share 2020 or something. So the motivation was if we actually had brought all these suites of different types of imagery, will they come? So we actually went ahead and said, this is the list that we've actually have promised. We'll be able to share it. And boy, did they ever come. This is just a small portion of the list of experiments that we did on this particular collect. All the way from human subjects and different types of change detection. There was a Kinesis Lake water object submerged. There was unmixing, lots and lots of different ones. And the point is there were tons of sub-experiments throughout the entire process. The word did get out. This was an RIT funded project, but the word did get out through a variety of our alumni that this was going on, and so we actually had quite a few partners as well. mostly bringing their own ASD instruments to help us with the ground support and to set up some of their own experiments. And I'm not going to go through any of the experiments. The main point of this is that there was a lot of different types, mostly on land, some in water as well. And this is just showing some of the different sites that we collected on. And the main site gives you just a feel for some of the different targets that we deployed. And some of the variety of different ones that were in the area. So I'd be remiss not to show a single spectra somehow in this, right? So this is just one of the many experiments and some of the different targets that we had out. It was a whole unmixing problem where we built these large quilts, for lack of a better term, of very precisely measured amounts of different colors and constituents patterns. Again, we had extensive ground truth GPS, all the imagery. We had 2 radio sound launches, lots of in-water samples as well, lots of ground truth. We had 3 ASD field spec, I believe they're field spec pros at the time. 1 ASD doing full sky irradiance measurements with the RCR for the entire day. And we had very, very large calibration targets. And we took a variety of measurements both throughout the day, both in reflectance and radiance mode for the different experiments. This is pretty much one of my main contributions, rather than organizing the troops, was actually to come up with the system of the data distribution after the fact. So not only is the data all freely available, the imagery, all the ground truth is available as well. And so for any one particular point in this GIS system, you click on a different type of icon, different type of experiment name, and automatically downloads the spectra that was taken from that point and all the ground images that were taken surrounding that point. So it's just a system that no matter, you can actually search through all the different types of imagery, but also through all of the ground truth that we collected, whether it be the ground-based LIDAR or the spectra or even the radio sound. So I just put this up there. There is a web page where you can actually get all the data as well. So I'm going to move forward. That was basically making data more accessible and integrated, a key component to actually solving that initial scenario. The present, what we just kind of finished working on primarily is for the Landsat 8, looking at coastal water studies. And I think that's pretty much where we are. A lot of us still are at this point where we're still just trying to validate remote sensing data. It's what we use the ASD on an almost daily basis to do. So this is a project by Javier. He just finished up, just started working down at NASA Goddard, but worked with him for the past 3-4 years on the use of Landsat 8 for monitoring freshwater and coastal waters. Obviously, I'm not going to go through his whole thesis, but what he actually did was actually look at Landsat 8 to actually derive different types of water constituents. So the chlorophyll, the CDOM, the suspended minerals. And not for really easy cases, but for the difficult cases on Lake Ontario. So for coastal waters, really turbid waters. And what he wanted to do was take a Landsat 8 image, see if he actually could produce chlorophyll maps, dissolved organic maps, and the suspended mineral maps. And again, why Landsat 8? We know that this is probably possible for hyperspectral. There's been lots of research. If you had an Abercine or hyperspectral sensor, you could actually do this. But why Landsat 8? Well, for one, we're on the Landsat 8 science team, so I guess there's some money and funding issues. Students like to get paid and they like to eat. So that's one of them, but also because Landsat 8 had a couple of new features. Not so great in the thermal, but awesome new features in the visible. It had a new blue band. It also had, obviously, a really great bit depth, and improved signal-to-noise ratio was the huge factor. And there's just 2 different examples. You probably really can't see in this example the difference between Landsat 5 and Landsat 8 is tremendous for water quality. So his study was basically to look, is this Landsat 8 actually improve? Can you actually start actually looking at just a few bands and actually still deduce what those different water constituents could be? We studied, again, for many, many years up at Lake Ontario. This is just the Rochester area. And we went through a variety of different experiments. Every clear Landsat day was, we tried an attempt to get out there, basically from May to November for 3 years. We collected data, and he actually basically ended up with 3 data sets out of probably trying about 60 times. So it is very cloudy in Rochester indeed. We collected remote sensing reflectances, water-leaving reflectance. We measured that and correlated that with water samples. So we actually did the lab analysis as well, looking at exactly all 3 of those constituents and what the actual values were, so that we could correlate that to the reflectance measurements. We went through a series of revisions and came up with a method to actually take our spectral measurements. And it's really quite comical because you do need to take a very conscious effort of actually making these measurements in very specific angles when you're dealing with water and taking your sky values as well. And when your waves are about 3 to 4 foot in height, those angles may not be quite what you think they are. So we definitely need to come up with some better ways to do that. This is just an example of why we love this area, I guess, despite the clouds, after complaining about all that. These are some of the different sites that we go. We actually split up in a handful of teams, and we trade our equipment off, go out in a large boat out into Lake Ontario, and then some canoes in some of the smaller ponds. But why we really like them is the diverse water types. In one specific day, we can get a huge variety of not only just the remote sensing reflectance values, but all those constituents. So I don't know if you can see, going back to this one, this is actually called Cranberry Pond. It can have a huge, huge amount of chlorophyll compared to any of the other water bodies. Anyways, they're very, very diverse. There's a couple of different reasons we won't go into it, but it gives us a really quick snapshot in one very small area of large different types of water. So I'm not going to talk about his whole thesis. There's references in the slides, but basically what he went through is he came up with a routine where he took the radiance from the satellite, spent a huge amount of effort dealing with all the atmospheric compensation over water, which was critical. Coupled the measurements that we took, the lab measurements, with the reflectance measurements that we took in the field, and used HydroLight to do the predictions. And so he did tons and tons of results, all his results going down to one specific day, one slide. It's not doing it justice. But basically what he did is actually was able to produce these maps. And not only was he able to produce these maps, he's got the ground truth, the spectra, and the lab analysis to actually compare and see how well could he actually estimate the chlorophyll, for example. So it's inching forward. Again, this has been done with hyperspectral. This is just using a few bands out of Landsat. So I just want to quickly go through one presentation that we actually have just started. So this research just started this fall. Student Ryan Ford and his advisor, Dr. Vodacek, they're looking at this exact problem of dealing with harmful algal blooms. I think you've all probably heard of the case last summer, where Toledo didn't have drinking water for days on end, basically because of a huge algal bloom in Lake Erie. Not only is it obviously a huge problem if it's your drinking water source, even if you come in contact with this and you have an open wound, you can actually get a very severe infection. You can also have liver damage. So it's pretty nasty stuff, something that we really need to start learning a lot more about. There's some major types that are found just in this area. The most common is this microcystis. It's a couple of other ones. Not all algal blooms are toxic, and that's what we're trying to look at. There's a whole series of why they actually cause. One of the latest ones is it quite often will occur right after a really high wind event. It actually is picking up a lot of the nutrients from the from the water body's floor, and mixing that up. In the late fall, that'll turn into a bloom. Again, not all blooms are toxic. So this is just one. I don't know if you can even see that, but it's a Landsat image. A couple of Finger Lakes in there. Some small regions where there actually are blooms, and actually there are confirmed cases from the New York DEC in these two regions at this time of those areas. And so what he's just starting to look at, again, just started in the past couple of months, looking at Landsat 8 and the cyanobacteria, extending basically what Javier did at the water constituents, seeing what he can actually learn from the satellite imagery. Going back to this image, doesn't take much to see that there's something really going on there, and we actually can see it with satellite imagery. We want to take it to the next step and actually look at it and see, can we look at the factors leading up to that bloom? Can we predict those blooms? And can we actually determine whether or not there's really something actually harmful in them, or are they just an algal bloom? So, unfortunately, we had a very large algal bloom in the north end of Kinesis Lake this past late October. And so he literally just started getting his hands wet and dirty, and actually started going out and collecting some measurements. So we took water samples, as well as obviously we went out and took specific spectra of this. So he's just at the beginning stage, what these actually look like, the different characteristics. This one here is basically all in a suspended mode, and there's just obviously in a much thicker. And he's really starting, as you can see, because he calls this scum. We probably will need to beef up that that terminology not too long. Again, we're in just the beginning state, but we actually were able to have a local company actually fly over this area with drones, and so we actually have some higher resolution imagery of this particular area as well. And we are coordinating with the regional DEC to see what kind of timelines they need and what are the exact products that they would actually use if they had them, and what kind of time frame they need those in. So again, my question is whether or not it's this application or your application. Are we there yet? Can we take spectral data and turn it into some kind of real-time system? If not, what are some of the factors that we need to fix? As I already pointed out, obviously we can't go around and scan things quite yet with like a tricorder and say, yes, there's definitely something poison in there. But I think we're getting really close, and I was quite intrigued by this device here. Haven't had one in my hand yet, but I'd like to try this one out. The ASD's very small, portable quality spec. Might be something good size for water regions. But I think quite often most of us are kind of still in this stage, and we're still kind of looking at the spectra and kind of scratching our head what we're actually looking at. And hopefully we'll get past that. So that is it. My contact information, most of you know who I am. It's just Nina and Pat here. And I'd like to also thank that many of our students have actually been the great recipients of the GETS instrument program. We've actually had loaners quite frequently. They don't always line up with the exact customs problems and the cloud problems, but we've actually been very fortunate to have our students be able to have some extra ASDs here at the university when we were really tight for projects. So thank you.
All right, ladies and gentlemen, thank you again for attending the event with us. If you'd like to learn more about the various application uses for ASD instruments or other specific applications as pertaining to our use, we have a webinar series this year. We'll have a new webinar every month. You can go to our ASD events section on our website at www.asdi.com, and you can register for those events as they appear. If you have any ASD related questions, please contact us via email at nir.info@panalytical.com. Thank you again for attending, and this concludes the event.